Well, having obtained the partition function for the rotational rigid rotator, let's use it to calculate a few quantities that shouldn't be too surprising to you from your previous classes. Just to recall, in the previous video we just obtained this expression for the partition function for the rigid rotator. And it's a very simple expression. It's just the temperature divided by the symmetry factor divided by the characteristic rotational temperature, or just the rotational temperature, which is a constant given by this one of these expressions. Pick whichever one you like or find the easiest to use. It varies a little bit from problem to problem. Sigma, of course, is the symmetry number, and T is the absolute temperature. Well, let's take a look at the average rotational energy for a heteroatomic diatomic molecule. So this would be, maybe something like NO, for nitrous oxide. Oh, is that NO2? Yeah, you guys are the chemists, so I'll let you sort that one out. But NO, or a CO, carbon monoxide. So it would be one of those, which the two molecules in this diatomic, or the two atoms in this diatomic molecule are different. And really that's just so I don't have to worry about the symmetry factor, and I'm going to be setting the symmetry factor up here to 1 because of my conditions I'm looking at. The rotational partition function, well, if you look at that, I use this one here, just and then I divide by it up here, and so that flips the denominator to the numerator and vice versa. So my rotational partition function now looks like this. And I can calculate the average value for rotators in this gas, these diatomic molecules. And as the expectation value of the energy, and we know that that's just given by kb t squared times the partial derivative of the natural log of that partition function, z rotation. Using this expression, I can write this as the sum of two logarithms. It's going to be the log of t plus the log of this number here. Again, I could have left that. It's really theta inverse over here. But just to emphasize, if you look at that, there's nothing there but constants. Boltzmann constant, Planck's constant, the moment of inertia of the molecule that we have. And we don't even really need that in this case. I kind of have dwelt on that probably too much, maybe, because in the overall scheme of things, by the time you take the partial derivative of this with respect to t, this goes out. There's no t in that. It's just all constants. Which is to say that for a given system, once you've calculated this rotational temperature, then it's going to be that for the duration of the problem or the duration of the calculation until you change the essentially the moment of inertia is the only thing it depends on. So until you go to a particle that has a different moment of inertia. So we're down to this. Partial derivative of this second term is just a constant, so it vanishes. And the partial derivative of the natural log of t, well, that one's easy from elementary calculus. That's just 1 over t. And the t's cancel, and so you get that the average energy of one of the rotators in this gas is kBt. If there's a capital N, if there's N such molecules in the system, and if we're looking only at the rotational part of the energy and part of the, obviously if there's molecules, they would have translational energies as well, but we're only focused on the rotational part in this section. But I can get the internal energy of the system, at least rotationally, is N times that rotational energy. And so N times Kb, we've seen a number of times, that's the number of moles of the substance times the ideal gas constant times T. So you probably have seen expressions like that for the rotational energy in previous courses. And for us, it allows us to calculate the specific heat at constant volume. I haven't dwelled too much on whether it's at constant volume or constant pressure, but when I take the partial derivative with respect to T, this this expression here is at constant volume. Z really depends on volume as well in general, and in this case it doesn't, but in general it does. And so when I say partial with respect to T, I'm treating everything else as a constant in there. In this case, it's if there were a volume term, it would be a volume. So this is actually the specific heat at constant volume, but just due to the rotational energy of this rotational system. And I have that up here. And so if I differentiate this with respect to T, I get Nr. That's the rotational contribution to the specific heats of the substance. Again, there can be a translational contribution. There can be a vibrational contribution. I can even have other contributions, but generally you consider translational and rotational in these. You may have seen this specified a little bit differently. And diatomic atoms or molecules has degrees of freedom for each contribution of 1/2 kBt. And in this case, there are 2 rotational degrees of freedom. If you look at, here's I have a heterogeneous diatomic molecule. There is a rotation of this whole molecule about the z-axis, but there's no moment of inertia there, and so that term is missing. And the ones that can rotate are either about this axis or about this axis. So we've got 2 rotational degrees of freedom, and there's 1/2 kBt, if you remember, per degree of freedom, or 1/2 R per degree of freedom to the specific heats. And that conforms to what we have in the previous 2, either on an atomic basis or on the basis of the solid or the gas as a whole, and that we've got 1/2 kBt per degree of freedom and 2 rotational degrees of freedom in this. So hopefully that's a trip down memory lane for rotational degrees of freedom for you. In this case, obtained via the partition function.